This video is on the ideal mechanical advantage of ramps and of screws. Please remember from one of the previous videos that ideal mechanical advantage, also known as IMA, is always going to be larger than the actual mechanical advantage because it ignores friction. It assumes that there is no friction in the world, thus making that mechanical advantage ideal or perfect. A ramp, also known as an inclined plane, is I think I don't need to explain very much what it is, but the word inclined plane means a flat surface. Inclined means at an angle, so it's a flat sloping surface. Ramps allow us to use less force to lift something to a height, but as you see in this first diagram here, the distance, and again the input is you, the distance that the person has to move that object to get it to the same height is larger than the distance that you would have to cover just to lift it. There's a trade-off in that I have to go apply my force for a longer distance, but I can apply less force, making it easier for me. Ramps is on ideal mechanical advantage of ramps and of screws. I'm not really going to talk about what a ramp is because that's something that we are all familiar with. We see them all over the place in the real world. A wheelchair ramp, a staircase is considered a ramp even though it has jagged edges. And so these are things that we see all the time. The thing about mechanical advantage, again, is that oftentimes there's a difference between the amount of force you apply and the distance that you apply that force over. As you can see from this diagram right here, using this ramp in the first example, to lift something to this height would take me a lot less force. It would take me a lot less force to use the ramp. But notice that the distance that I apply that force is much longer than if I were to just lift it straight up. And so there is a trade-off between distance and force when it comes to using any kind of simple machine. The ramps, ideal mechanical advantage of a ramp is the length of the ramp divided by the height of the ramp. The length being the long way up the surface that you are using to pull the object or push the object, divided by the actual height off the ground that it reaches. As with all other mechanical advantages, there is no units because if I look at this example, I would be taking 10 meters divided by 1 meter, and my meters would disappear on both of those, giving me an ideal mechanical advantage of 10. Now remember also that ideal mechanical advantage is also always larger than we would actually get if we were to measure the mechanical advantage using forces, because there is friction in the real world, and that's the difference between ideal and actual. So a quick couple of examples using a ramp. So if I want to find the mechanical advantage of this ramp, I can see, I already put the equation down here in the corner for you, that we have the length being 4 meters and the height being 0.5 meters. So I would have 4 meters divided by 0.5 meters. And this will give me a mechanical advantage of 8. Which again, what that means is that I seem like I am 8 times stronger when I would use a ramp that is this length. It would allow me to lift something a lot easier, 8 times easier than if I were to lift it straight up. Also remembering that there is no units because meters and meters will cancel out in this situation. Again, I always give you examples where you're not actually solving for the mechanical advantage, that you're solving for something else. So in this example with this ramp, it says that the mechanical advantage is 3.5. So this is your IMA. And it shows you here 12 meters, and that is the length of the ramp. So we need to find the height of the ramp. So I know that 3.5 is equal to 12 meters over height. Or again, if you like the triangle, I would have the IMA in the corner on the bottom. I would have height on the bottom, and I would have length at the top. I know that's not super clear, but hopefully you're listening to what I say, not just looking. So if I am looking at how I would solve this, this would actually be 12.5 meters divided by 3.5. Sorry, I have to actually get my calculator out to do this. And I would get an answer of 3.43. And again, this is a height. So my label would be in meters because heights, lengths, all those distances still have units. It's just mechanical advantage that does not. Okay. If I look then at a screw is simply a rotating ramp. You take a ramp and you rotate it or you twist it into a coil and you now have a screw. So an example of a screw obviously would be a screw, but also a spiral staircase would be a screw, road that winds back and forth, a switchback road on a mountain to help you get to the top easier. Those would all be considered screws. As you can see in the corner, IMA is the head circumference divided by the thread width. And the threads are these little, where the ramps connect. And so it'd be the distance between the threads is your thread width. Head circumference would obviously be the top where you use the screwdriver, the circumference of that. I will never make you calculate the circumference. Like I won't have you do that using pi to calculate it. I will always give you the head circumference or just have you calculate it using IMA and thread width. So using the formula, we can see that says if a screw has a head circumference of 1.5, notice that I do abbreviate so that you don't have to write out those words when you're showing your formula. Has 1.5 centimeters, thread width of 0.5 centimeters. So this is your thread width. What is the mechanical advantage of this screw? Well, I've already put the equation here for you, but remember that when you are doing the assignments, you need to put your equation in. I would take 1.5 centimeters divided by 0.5 centimeters. And I would find this to be a mechanical advantage of 3. So this particular screw would multiply my force by 3. If I do one more example, again, always solving for something other than the IMA. If the screw has a mechanical advantage of 7, so there's your IMA, and a thread width of 0.15 centimeters. Oh, sorry. This would just be thread width. Be easier if I did that way. What would be the head circumference of the screw? And just like every other time we've done these, you have the option of using the equation as is or thinking about what would this triangle look like. This triangle would have set head circumference at the top. I'd have IMA in one corner and thread width in the other. So even if I decide to use this equation as is, I would have 7, which is the mechanical advantage, is equal to the head circumference over 0.15 centimeters. Either way you set it up, you would end up multiplying 7 times 0.15 to get an answer of head circumference of 1.05, and again, centimeters, because I have centimeters here, I need centimeters on my answer so that I have both of those done. So that would be it for ramps and screws. There will be another video or another video or two for the remaining simple machines that are on our checklist.